So let's talk about matrix multiplication. Suppose I have an m by n matrix A and an n by p matrix B. Multiplication by B is going to define a linear transformation from Rp to Rn, and multiplication by A will go from Rn to Rm. And so we showed already the composition of linear transformations is linear, and from maps from Rp to Rm that are linear, they're going to be represented by multiplication by some matrix. And so let's call that matrix C. Let's try to trace through what happens to a vector in Rp. So suppose we have x as x1 up to xp, a vector in Rp. If I multiply by b, by definition, I'm going to get x1 times the first column of b plus x2 times the second, and so on down to x, the last column times the pth column of b. And now I'm going to take that vector and multiply it by this matrix A, which matrix vector product is going to distribute across vector addition. And so that's going to give us A times x1 b1 plus all the way out to A times xp bp, which, if I just regroup things a little bit, is going to be x1 times A times the first column of B plus x2 times A times the second column of B, all the way down to xp times A times the pth column of B. Which means if I think about the columns of C as C1 up to CP, C1 is A times B1, C2 is A times B2, and so on down to CP is A times BP. In other words, C has columns AB1, AB2, all the way out to ABP. And now here's the great math trick. Right? So this is a really good trick. Basically, you can get a theorem, a result, if you just make the right definition. So how does this go? Well, notice that A times B times x is equal to C times x. And we just computed what C was. So if we define a matrix product A times B to be what we computed for that matrix C, then the result that we get, the theorem that we get almost for free, is that A times B times x is equal to the matrix product A times B times x. It's a fantastic math trick. So here's our definition. If A is an m by n matrix and B is an n by p matrix, then the product, denoted AB by concatenation, is the m by p matrix whose columns are AB1, AB2, all the way out to ABP. Equivalently, if you want to think about it in terms of components, if A has ij entry Aij, and B has ij entry Bij, then the ijth entry of AB is just the sum k equals 1 to n, Ain times Bnj. So let's take a look at an example, an explicit computation. Let's compute the product of these two matrices. So I'm going to take the first column of the matrix on the right. We've been calling it B. So I take this 4, 1, and I'm going to view it sideways because I want to use it as the coefficients on the columns of this vector A. Right? And so I get 4 times negative 2, or sorry, 4 minus 2 as this top entry, and 12 plus 5 on the second. And now I'm going to repeat it for the second column of B and put the resulting things here in yellow and green. So I get 3 plus 0 and 9 plus 0. And finally, for the third column, I get 2 plus 2 and a 6 minus 5. And then I just do the arithmetic and see that the matrix product is 2, 3, 4, 17, 9, 1. a few warnings. This matrix product, it does behave like a product in some ways, but in other ways it's different than the products that you're used to in the real numbers. So for example, if I just give you two arbitrary size matrices, you can't just multiply them together. Right? You need an m by n and an n by p. You need this entry to agree. And in that case, you can multiply them, and the resulting matrix is an m by p matrix. If they don't agree, then you can't multiply the two matrices together. 2, if A times B equals A times C, you cannot conclude that B equals C. And 3, if AB is the zero matrix, so we'll denote the zero matrix maybe with a 0 and an underline. If AB is the zero matrix, you cannot conclude that A equals 0 or B equals 0. It might be the case that neither one is 0, but they multiply to the zero matrix. 4, order matters. So A times B is not the same as B times A.